Greetings everyone, and welcome to KLIPPEL's free webinar series, Acoustical Measurement of Sound System Equipment according to IEC 60268-21. My name is Kent Peterson, coming to you from Warquin in St. Paul, Minnesota, your home for KLIPPEL sales and support in the US. Today's 11th seminar, entitled Pitfalls in Testing Wireless Audio Devices, has been much anticipated. I've heard from a lot of you that you were looking forward to this seminar expressly, as it is such a growing and strong segment in our lives. Pardon me. We often discuss this at Warquin as a bit of a renaissance in home listening. It often reminds me of the explosion of high fidelity in the 60s and 70s, if you're old enough to remember that. I certainly remember the 70s and remember those great big home console systems. I remember my dad's, and I think I used it more than he did after a while. So that's even extended into the recording studio, which is interesting. I now have a selection of Bluetooth systems, the most popular ones, I guess, right next to my mix monitors now. They've also forced a lot of mix engineers to reconsider checking their mixes in mono. How about that? Who listens to mono anymore? Well, everybody does. And those of you in the business should take that in consideration. I've talked to some young mix engineers about it, and they look at me like I'm crazy until I hold up a single Bluetooth speaker, and then they get it. This is how we listen to music at home, or at least a large part of the population. I think you'd agree. So let's get going. Remember to use the question and answer input below, and not the chat window, so we can answer your questions in the order they show up. Also engage in the polls. We love to see your opinions and choices. And as always, enough of me already. Nobody likes to see me chatting too much. Let's turn it over to the professor, Dr. Wolfgang KLIPPEL. Welcome back from your short holiday, doctor. We are happy to see your face again.
Yeah, I'm back with new forces, back to our long series of webinars. Before I'm starting with a new topic here, let's see, why is he not coming? Yeah, I give a short summary on the previous section. Actually, we spent a lot of sessions on physical measurements here. That means that was, of course, related to the microphone measurement. We have spoken about measuring the total output, and here with the holographic scanning. And then we dived a little bit deeper into the different distortion measurements. That means total harmonic distortion, intermodulation distortion, compression, and our last session was impulsive distortion measurement, more or less rub and buzz. Now we have almost finished the physical measurements, and I have given or tried to give a good overview on the new measurement techniques, but one thing is missing. The new standard also is just written for new wireless transmission techniques, and we get completely new problems, and they are now considered in this session here. Yeah, that's the whole idea. Pitfalls in testing wireless audio devices. Okay. What is our topic in detail? We have new challenges in modern audio devices. I'm speaking quite shortly about this as an introduction. And we have to provide new measurement solutions for R&D and QC applications. But we have new problems. Nothing is really perfect, and we have to solve them. And that's more or less a topic. And that should be very practical. I give some tips how to detect the problems and how to solve them, and some demos. Okay, we are starting with the first poll. Which transmission way do you prefer today, now, for testing active audio systems? You can still use your analog cable. That's reliable, you know that. But you can use a digital cable with Toslink and LAN and something like that. But we have many audio products with a wireless connection in the different ways. Here, Bluetooth is very popular. And of course, we have some devices where there's no wireless and cable connection. We have to come really with an audio file, with a WAV file, and that is also an interesting way to provide the stimulus or the recorded response back to our analysis. Yeah, and now I'm looking here to the results. It was correct. I see it on the spot here on the result. 70% still are using an analog connection because it's usually there. It's reliable. We know the problems. It's usually noise or other different things. We are educated to cope with that. But B is already here the digital cable. That's also quite reliable. I also enjoy it. And of course, the other wireless connections, they are at the moment less popular. Also the digital cable was with 50%, and then comes the W-lane with 5% and Bluetooth with 10%, and the asynchronous transmission, that is also 10%. So that's what I a little bit expected. So my practice is more or less in common what you are doing. Yeah, let's go on. Let's illustrate the different techniques. Here we are in the old ways, the conventional way. We have the closed loop testing. It's analog. We go here, if I'm using the KLIPPEL analyzer, we take the output, feeding that to the active speaker, and have a conventional microphone to the input. Yeah, with the Bluetooth, many things are changed. It's not perfect. It's very convenient. It's available in many modern devices, but it has a short range of communication. We have a pairing process and a connection process that sometimes takes some time. And for end-of-line testing, this is a small problem. And of course, some solutions are required for that. Yeah, we have different versions from the Bluetooth audio, the classic one, and the low energy version, and something like that. And of course, there are different audio profiles, so it's a little bit confusing. Yeah? Many codecs are available, and some others are coming, most likely, and so on. So that's a world by itself. Then we have a closed, here you see the closed loop testing with Bluetooth. What we are preferring for all our existing modules and existing hardware. That's why we are taking the analog output from the KLIPPEL analyzer. We are going into a Bluetooth transmitter and sending the digital signal to our Bluetooth speaker. Yeah, and doing the measurement with a conventional external microphone. Yeah, this is here our MegaSegun U980. It's a quite robust, quite nice solution. You can configure that via USB. I show it later, how handy it is. It is now nicely integrated in our QC and R&D software. Yeah, it supports at the moment Bluetooth 4.2 and most of the major profiles and so on. And you can connect this not only to the new KA3, but also to the production analyzer and to the old distortion analyzer. So that's quite nice. And here you see a typical complex setup, what is required for measuring Bluetooth devices. Here we have a Bluetooth speaker, and we are using here a test microphone and maybe an optional test microphone for moving that with our hand. But what is the main thing? That is how we are providing this stimulus to the Bluetooth speaker. It goes more or less from our generator inside our software to the KA3, and from the output here we are going into the MegaSegun, and then comes the wireless transmission. Yeah. At the same, we get here the microphone signal from inside the Bluetooth speaker. We going back in the same path, but reversely. Also first via MegaSegun and then via the K3. It's a very simple, very robust solution. That's quite convenient for R&D. The same here for a Bluetooth headset. It looks very similar, but we can also operate here some additional speaker outside for simulating some ambient sound for testing and so on. So that's also interesting, say for ANC testing of headphones and something like that. Yeah, so it's the conclusion, it is part of our daily life. But we have another scenario, what is quite interesting because it is more robust than and sometimes more universal than Bluetooth. That's the open loop testing. So we have an independent stimulus playback. The generator is not directly in the loop. That means we have no K3. You get from our PC directly maybe the audio file via a cloud service, maybe into the smart speaker. You are playing that inside the generator and doing your measurement. What is also very convenient is to use your smartphone as an external player. Why? Because there's usually the most updated codecs inside. Everything is supported. That's a very nice way to measure always the most recent audio devices. So this is a very nice, very simple combination, but new challenges for the measurement technique. Yeah, what are the problems in open loop testing? Sorry, maybe it's a little bit too loud. Maybe it's acceptable. Here you see we are playing inside our smartphone or directly in the audio device our chirp, yeah, again and again. Maybe it's a little bit embarrassing. And we are using maybe as a microphone and our hardware or a digital microphone, it doesn't matter, for recording the waveform. And if we are calculating the transfer function between the stimulus, which is asynchronous, and the recorded waveform from the microphone, we see that the impulse response occurs at any time here within our recorded stimulus length. That's here about 300 milliseconds. So we have actually an arbitrary latency or time delay in our measured response. Yeah. How to detect this variable delay? So there are two interesting solutions of that. First is a pure software solution, and that's the external synchronization. What is the idea here? We have here our stimulus. The stimulus may be also shaped. Think about that. You would like to reduce a low frequency signal or doing a small signal measurement at very low level. Maybe then the synchronization would be quite difficult. To be independent from the amplitude of the stimulus, whatever you are doing, and even if you make a noise floor measurement, we are using here an additional signal. That's a sync signal. But it's not a primitive signal like a 1 or 2 tone signal. We are using here a noise signal where we can, in a very nice way, encrypt an ID. So we know very much the ID of this whole stimulus here, of this combination. And in the measurement system, we can check that the right stimulus is played from the external player and that we are doing the right measurement. That's actually required for many applications. Yeah, and then we can provide a very, very precise synchronization of our measured response. That's one solution. Another solution is if we have, for instance, a Bluetooth device, we have not only the delay problem, but we have also a clock jitter problem. And the clock jitter problem is very bad. That's why we need an even better way or an alternative way to synchronize the stimulus. Here we are doing that completely on the outside, also in the acoustical sound field, by using a second microphone. Yeah, this is a measurement microphone, maybe the important one, maybe moving here with a near field scanner around the Bluetooth device. And this second one here is at a fixed position. That's our reference microphone. Yeah, here the chirp is always played. Yeah, that's our scanning microphone, and that's the reference microphone. And by comparing more or less the phase shift between the signal detected in the measurement microphone and detected in the reference microphone, we get the important information which we need for our holographic output-based measurement. Oh, that works quite nice. Here it is illustrated. That's stimulus. That's the second. That's signal from, or the impulse response from the second measurement, and we know this time delay, and we are subtracting that from the measured one. Yeah. We can also remove any artifacts from the, or some other artifacts from the Bluetooth path and so on. So it's very useful to use a second microphone, but that's here mainly used for synchronization. What are the problems? Here one example from the holographic measurement. We have no analog input for the smart speaker. We have a very long and varying time delay, a lot of latency, and the external synchronization is not applicable, and the solution is the second microphone here. Yeah, and it provides very, very high accuracy, up to 20 kilohertz for the phase measurement. We need that for the holographic processing, and we can also use this microphone for detecting dropouts in the somewhere in the connection, or sample rate drift, ambient noise, and other problems. Why? Because we can compare this measured signal at the reference mic with the first measurement we did. And if we find significant differences, then we know maybe this microphone position is changed, or ambient noise is influencing or corrupting our measurement, or some other things happened. Yeah, that's very simple. It's robust. It should be not a very expensive microphone, an inexpensive microphone. It's a very good solution. Yeah, here you see how it works from the whole measurement. So no, we have here no tone. No, it doesn't matter. So that means this device plays always the same stimulus, and we are doing here a lot of asynchronous measurements. Okay, that's maybe enough. A new challenge, MEMS microphones. Here is a very special MEMS microphone developed here in our company. It's a little bit larger than you see the different microphones here. What is the idea here? We would like to measure very precisely the directivity pattern from all the different transducers, also microphone transducers here in the MEMS microphone. And this is not so easy, especially if you are moving here the microphone and so on. And a very good idea is to use, to a point more or less, or here comes first the requirements. We need sufficient accuracy in the absolute transfer functions, but this may be affected by the setup, and we need very high accuracy between the microphones. That's important for beam steering. So in the relative amplitude and phase response. Yeah, and the solution is we appoint one microphone here as a reference microphone. You can use any one of those as a reference microphone, and you are recording and transmitting at least two signals from one selected test microphone and from the reference microphone. And then you can calculate the relative phase shift between the microphones. Yeah, and you have an additional benefit to see whether something is happening with the test stimulus and so on. And maybe you can also compensate for the frequency response of the loudspeaker. Yeah, here an overview how we are, say, bringing our sometimes old modules into the new world ready for Bluetooth and other things. Here the TRF is more or less 15 years old, but we are still working on that. You see it very soon. So it's now ready for the closed loop testing, for the open loop testing. With this, we have some problems with the open loop testing. Why? Because we can step the voltage, we can change the frequency, and we have to transmit many wave files, and nobody will like that. So that makes actually not much sense. With a tone burst, it's the same. It's a stepping technique. So we are changing a lot here the voltage. This makes not much sense. But for the multitone testing, here it would be a very good idea, and we are working on that, and it's planned also to export the stimulus and to play the stimulus and live here with the open loop testing that will come. But it is already nicely implemented here in the closed loop setup. Yeah, the multitone measurement is very, very important. We need it later on for benchmarking of products, and it is one of the, and for rating the SPL max. So it's a quite important measurement. That's why we are spending some significant work on that. Yeah, and of course, for the near field scanner and for the traditional polar measurements, we are supporting that. Yeah. Wireless testing in production, that's a little bit a pain, because if we would like to measure at the end of line as fast and comprehensive as we can, we need high sensitivity for defect, but actually the Bluetooth connection is not the most perfect transmission. And it should be also simple to use. So the critical issues are actually the automatic pairing, what requires some time. And it should be a very smooth Bluetooth setup. We have here different QC solutions in addition to the R&D solution to minimize timing and so on. What is very nice is the synchronization, the delay detection and compensation, where we have our special noise synchronization signal. Yeah. Here you see everything for the most important acoustical measurement is supported here in the QC for the open loop testing, for the closed loop setup. If you need any detailed information about R&D and QC, please contact our support. So I keep it quite short. But now I'm coming in the next poll to the problems. And maybe you are mostly interested in that. What kind of problems are coming up? How can we detect them? And how can we solve them? But I asked you first about the problems. Of course, maybe you will not choose here number A. I spoke too much about the problems. Maybe you will not click on that. But here we have large latency delay. I spoke a little bit about this. Varying latency versus time, jitter, clock, drift, sampling rate, mismatch, dropouts, interpolated sample, and others. So the main question here is which problem you see in your daily work and which are really a pain for you. So we get already some results. And the winner is actually number C, varying latency versus time. It is 37%. Then large latency is with 20% the next one. And then comes actually dropouts, interpolated sample with 20%. And then we have only with 11% jitter, clock drifts, and something like that. Yeah. We have also one person who said he has not much problems. Yeah. Here you see now the latency. That's one big problem. The latency is so large, in this case here 300 milliseconds, that we are really missing the late part of the response, which are here actually the high frequency signals. You see it here in the results. Suddenly your fundamental drops down. That's a very clear indicator that maybe the full stimulus has not arrived at the microphone. Yeah, missing the late response. What is the conclusion? The easiest way is you play multiple loops of the chirp of your stimulus, and you cut out a complete part of the stimulus. Yeah, here you see our solution for the 3D measurements. That's in the disk. You can, here we have also a pre-loop where you can really in seconds require how long the pre-excitation time should be. That's here half a second, but you can extend that maybe to 5 or 3 seconds, but keep it as short as you can, that you then recording automatically a complete response. So that's one solution. In the transfer function, you should use in the normal way at least one pre-loop to ensure that you have, that's usually enough for most latency problems. Then we can cut out a complete response. But you see it's already delayed. So we are cutting not out at the beginning of the stimulus, but just in the middle and wrapping the signal, which generates also some problems. So use here the pre-loop, put one into that, and you are safe. Yeah, then we can use here the sync signal. That is a broadband signal, as I told you. You can make it quite short. It's maybe 200 milliseconds long. You can even make it shorter. We can code in this short noise signal quite easily here our ID. So that means it is a very good signal for very fast end-of-line testing. Yeah. So that's a pseudo-random signal. What are the benefits? You have no limitation with the latency. It might be very long, multiple seconds, even longer. It's the best for the open loop testing, and it's also very good for fast end-of-line testing. And you have an identifier in it, and we can make an automatic linking from the stimulus and the analysis. So detecting what kind of analysis should be applied to the recorded signal, or telling you there's a mismatch with the sample rate. Yeah, that is also possible. Yeah, let's do the first demo for that. I'm using here, I'm going to the, let's see what happens here. Yeah, okay, I'm now here in the DB lab. Here, I'm now in this section wireless testing. I have already paired that. Maybe I'm pressing, can you, or maybe we are showing this is a setup. Andrew, please switch on the camera. Okay, we have here again our Bluetooth device. We are powering the device. I could remove here the USB cable to stop the powering, but maybe it's convenient to keep the powering on. That's our MegaSegun, where we are doing the transmission of the stimulus. We are using for recording this microphone here. And now I'm starting here the pairing mode. Yeah, and now I'm starting here again our Bluetooth pairing. So I'm clicking on that, and now you see that here the pairing process runs automatically. Actually, it's completely automatic. It could be also a different Bluetooth device, and now it's connected, now it's paired. The timing comes more or less from the Bluetooth device. Some Bluetooth devices are a little bit faster, but it's a very, very easy way. We get here also information from the Bluetooth device. That's it. And now we can immediately go to our QC. Actually, for the QC, we have other ways for doing that, but I show it now in the context of R&D measurements. If you would like to use a QC measurement system also for R&D purpose, then this is here the right way for doing that. So I'm going into that from the R&D. Usually for QC, we have a different entrains. We are using the QC starting tools. Yeah, and now here's my chirp init. I'm measuring here from 20 Hertz to 20 kilohertz. I'm using here this special noise identifier for the external synchronization, which is optimized for high frequency dots. And now I can press a button and yeah, and maybe you have heard, I press it again. There's a very short noise signal and then it's our fast testing. Okay, that's it. So we get, maybe I duplicate here the measurement, duplicate the measurement here, and I do it also in the phase to show you some first problem. Here this is duplicated now, and now I'm repeating the measurement. Then you see that the amplitude response is quite nice. Here it's identical with the first one. Here where the signal to noise ratio is not good enough, we see some deviation. But look to the phase. It's fine at lower frequencies, not here where we have again noise problems, but look to higher frequencies. Yeah, that's quite it. The interesting thing is that is not a time delay, not a latency problem. That's a jitter problem from the clock in the Bluetooth transmission. Sometimes the samples arrive a little bit earlier and sometimes a little bit later. They are doing that to have in the mean the right number of samples to play more or less the audio signal without any dropouts and so on. So you have to pay for that. So we have a minor problem here in the phase response. But this problem here in the phase response is so bad from Bluetooth device, we could not do holographic measurements with that. That's why we are using the second microphone where we are immune even with a Bluetooth connection. So that's more or less my message from this experiment. Do you have any questions to that?
No question. It's just basically a comment, and
yeah.
And it's just encountering problems with poor sample rate conversions, causing aliasing, anti-aliasing. Mm-hmm. Yeah, that's a problem that we experience as well.
Yeah, that's true. That actually you try to adjust the sample rate, you are resampling that, then you get again and again new problems. Varying latency. So that's our problem here. We did actually statistics on the Bluetooth transmission. We have a constant latency part, as maybe the mean value here, yeah, and then you see the variance. It is quite significant. Look to that. The same device, the same setup, only in QC, doing the measurement again and again. So it might be 130 milliseconds or almost 200. So, and then we have still a jitter problem if we have a connection that is usually a little bit smaller. No? So this is a quite large variance. It's 35 milliseconds and acoustically 12 meters. So that's a big problem. So that affects, of course, the phase response. It would be a killer for the holographic measurement. With the holographic one, we have also the jitter problem. Yeah. Yeah, related to other problems, dropout, sample rate drifts, that depends on the ways how the audio device tries to cope with that. Yeah. Solution, second microphone, the near field for coherent scanning data. That's a very good idea. Yeah, now we are coming to the delicate things that is the jitter, the clock drifts, and some other sampling rate mismatch. Here it is illustrated. We are playing here our stimulus again and again. And here something that could be here for averaging or something like that. And that's the response. And you see the response is a little bit longer than the stimulus. So if we are doing our processing, yeah, we have a problem. This problem never occurs in normal hardware connection, cable connection, but for in the digital domain now, it's very, very critical why we are doing a frequency transformation. Yeah, This signal here is played a little bit slower than the stimulus, the original stimulus, so all the frequencies are at lower frequencies. Actually, if we are making a coherence measurement between this signal and that, we find out nothing is coherent. So the two signals, they are, or this signal is actually not generated by this source. So that's quite bad for non-coherence, incoherence measurements. Yeah, and what is the last bad thing? The delay becomes worse over time. So that means if your stimulus is long, you get not a better resolution, you get more and more problems. Yeah, and averaging is actually not a good idea. Yeah. Resampling or sample rate correction is required. Here, generating dropouts or some interpolations generates new problems, but can help a little bit. But that are the problems. Yeah. What are the consequences for the sample rate drift? That's now the jitter, more or less. It degrades the accuracy. We have problems with the frequency detection. We get different frequencies in the response, and we get severe problems separating nonlinear distortion from the loudspeaker from the fundamental. Yeah, so it kills or degrades the performance of our distortion measurement. Yeah, and also the phase measurement. And that's very critical for the multitone measurements, which is so nice for many applications and works so beautiful for an analog input and an analog connection. Here you see our fundamentals. They are very distinct lines. Yeah, we can look down here easily for an analog cable minus 90, 100 dB, and then we find here the speaker distortions and the noise. Yeah, if we are doing the same technique here for a multitone distortion, the fundamental is more or less the same, but look here to the to some distortions which are very close to the fundamentals, then you will see that at higher frequency we get a lot of distortion. What is the cause of that? Actually, the part of the fundamentals are now moved into the neighboring bin and are interpreted as multitone distortion. So it's actually a fundamental component. Yeah, that has a consequence that the original fundamental here in green has a reduced level. Some energy is missing, and the distortions are very, very high, unrealistic high, and they are not generated by the speaker. The distortions which are a little bit more far away from the fundamental, they are filling here the speaker distortion. Here you see it. And that's very similar to the normal speaker distortions. But the bad news is here some distortion lines, they are not right, not correct, and they are generating at higher frequencies 40 dB more distortions. Yeah. How can you avoid that? A very fast remedy is reduce the length of the stimulus. Make it as short as you can. Maybe with half a second you can survive, but then you sacrifice, then you get a poorer frequency resolution. Stop long averaging and avoiding wrapping around the recorded time signal in the FFT, because then the two signals at the ends, they will not fit together. So they are maybe on different levels because they are coming from different samples. Yeah. So maybe avoid long averaging is always a good idea for some wireless testing. Here you see a single sweep contra a chirp with 4 averages. With the averaging, you are improving here the signal to noise ratio in this region, but you are generating new problems at higher frequencies. If you see something like that, think about averaging. Stop that. It makes, or find the right way to resample the signal or other things. Yeah, the next problem is measuring relatively fast. We need for the holographic measurement a fast measurement. So we would like to play, here's the stimulus only 2 times, but not 10 times and something like that. And we will not wait a lot, we will not use the synchronization and so on. Then we come to the idea, cutting out only 1 period and wrap it around in the FFT. But if we are cutting the recorded signal, not at the end of the chirp and not at the beginning, but in the middle of the signal here and here, then we are generating, if there's a sample rate drift, a small click here at a certain position in the measurement. So that means the 2 signals at the end, they are fitting not together. Yeah. So you get maybe a response, an error in the distortion, and actually it's too critical for rub and bust testing. What is a better idea? To cut out the signal just at the beginning of the chirp in the response and at the end of the chirp. Here usually the signal decays because the sound pressure goes down, and we can nicely connect the 2 ends of that. They are not important for our analysis. They will not disturb the measurement. So that's a very nice idea, very effective from the measurement. You can make fast measurement and you avoid impulsive artifacts. It's good for rub and bust measurement. But you need an asynchronous processing. We need actually 2 chirps, to have enough signal. And you can activate our asynchronous processing here by setting here the checkbox in the DRF, and then we are automatically activating a pre-loop. We are playing the stimulus in each main loop twice, and then now we have 4 recorded signal where we can easily do as fast as we get here the microphone signal, the right processing. And we are detecting the time delay. We are moving our window just to the right position and cut it where we are generating no artifacts and no impulses for the rub and bust testing. That works quite nice. And what is the impact? If we are cutting the signal in the wrong way, here you see it, then we have generated in the time frequency plot a click which contains spectral component at low frequencies and at high frequencies. Okay, and here with this technique, we are completely free. That's like an analog measurement. That works quite nice. Similar problems with the dropouts, the glitches in the interpolation can be always checked if we are exploiting more or less multiple stimuli. Also we are playing out the chirps 2 times, 3 times, comparing the results and checking whether something is wrong and so on. So that's the best way for coping with that. Okay, and you can always check that the results, and we recommend this for the daily life. Do also on your side the measurement, if you have the time, again, and compare the results to check that there are no dropouts, glitches, or any other interpolation artifacts in your measurement. No? That's the best way. Usually those artifacts are random, they are not repeatable, so they can be easily detected if you are making a second measurement. Okay, and compare the result. Okay, the open loop testing, that means with a stimulus transferred via the wave file into your Bluetooth devices, the best way to avoid in the excitation any problems. Then you are safe with your stimulus, and then you have good chances for loose particles, which generate similar symptoms here in the measurement, like dropouts and glitches. Do you have any questions to that?
No, I think everybody's taking it in.
Yeah. Now let's
chin scratching.
Yeah. Now here to the multitone distortion. Here you see already the what we are doing. That's here the M-tone in normal mode, and here with a new way how we are compensating for this problem. Actually, we are detecting the sample rate shift. We are doing, here you see it, that's the first step, detection that something is wrong with our sample rate. And then we are compensating for that in multiple ways. So we make a resampling, and we have to insert a certain tolerance for jitter. So, and then we are completely free from those artifacts. And I would like to show that here in the measurement. I clean up a little bit my screen. We are coming first to the transfer function measurement. That's here a typical, is that, no, I'm still in the QC measurement. So that's a standard measurement from the TRF. Yeah, it's a single sweep. You are very impatient. You expect for analog connection, it's not a problem. Not much delay in the measurement. And if you start the measurement on the Bluetooth device, so we played only one stimulus, but you see here already in the waveform, no signal at the beginning. Also that's a recorded waveform here from the microphone. There's no signal. And you see a huge delay here in the impulse response. Yeah, it's at about 130 milliseconds. And you see, and the consequence is that we have not recorded the end of our stimulus, also the reproduced stimulus, and we are missing data here at higher frequency. So that's quite bad. To avoid that, it's very simple in the TRF. You just activate here the asynchronous measurement. Yeah, then we automatically put one pre-loop into that, and we ensure that you have only one pre. Well, I don't know whether you can. Let's check that. I have never tried that. Yeah, you can increase that, but it's not necessary. Keep it as short as you can. We are taking usually care of that. So now the asynchronous measurements runs. So we have detected four measurements. We are showing you only one recorded stimulus. Here you see the wrapping, the unwrapping is not done yet, but we detected the time delay accurately. Here in the processing, you find it 128 milliseconds. We are going in the four recorded signals just to the right position and cutting it out. And we are checking that there's no dropout in the different recording measurements. We are comparing the different recorded waveforms and ensure that we have a minimum of artifacts in the output. Okay, that's the TRF. Do you have any questions to that?
Nope, not at this time.
Okay, then let's come to the multitone testing. That's a very nice, exciting measurement. Let's start here with a normal measurement stimulus. Here you see the clock drift tolerance is not activated. Yeah, I assume everything is analog. Yeah, let's do the measurement here. Okay, here our stimulus, maybe I show the stimulus in the time domain. It's a noise-like signal, yeah, and that's the stimulus spectrum. We have here some tones at a certain distance, yeah. So it's a perfect stimulus, but what we get is not perfect. Here you see the recorded spectrum. We see here the fundamental. Okay, that's an amplitude response. I have not applied here a room compensation for that. That's not activated. That's why we see here some room reflections. Yeah, and this is the noise floor from the first noise floor measurement. And that's quite nice here. Andrew is speaking not a lot and makes no noise, so I was quiet, so we are almost 60 dB down. Here is the tonal component, maybe from the monitor, maybe here you see it here, or I zoom into that. Here, this is that's a tonal component here in my measurement room. You can nicely detect that, but something is wrong with the distortion. That is here the distortion. Here you see they are quite small at lower frequencies, and then they are rising here up to 60 dB. There's only a difference of 15 dB to the fundamental at higher frequencies. If I zoom into that, then here is the fundamental, and here is more or less that the fundamental component already occupies or contributes to the neighboring bin, and this is interpreted as some kind of distortion. The other stuff here, that is really from our loudspeaker, from the Bluetooth speaker. But if we are in a formal way cutting out the distortion, that is here the final result, you see that the multitone distortion are usually minus 50 dB, but they are going up to minus 20 dB at higher frequencies. That's not correct. The true response should be somewhere here, minus 45. Yeah, it becomes worse if I'm using a 5 seconds measurement. Maybe there's no need to repeat that. Here we are now very high. Look to that. Here the whole measurement is already has not much value. Yeah, so we have a lot of distortion already at 1 kilohertz and so on. It becomes worse over time. Yeah. And now we can activate here our jitter tolerance. Yeah, I did it. And now I'm starting the measurement. You will see that the measurement will be not longer. It's fast as usual, but we are doing a special post-processing. What is here you see the distortions are now down at minus 55, 50 dB. Yeah, that's the result we expect. And here also, here are no special lines close to the fundamental. We have separated them and have not considered them in the measurement. But we did much more. We detected actually the sample rate mismatch. Sorry, it's already compensated. That's why it's 0. Okay, I'm searching here. Let's see. No, here is a window. I don't find it where you see really the mismatch. Oh no, it's this. No. It's at 5 seconds, it comes up. Let's look to the tolerance at 5 seconds. Then here our sample rate deviation can be detected because that's only the fixed parts, the fixed samples, so the integer part. So that's far below than 1%, far below than 1 promille. It is more or less 5 samples, a 5 sample mismatch, generating this big problem here in the measurement. And you see the multitone distortion is very sensitive for any sample rate mismatch, and that should be compensated. Yeah, that works, that's easy, that's robust. Do you have any questions to that?
None at this time. I think everybody's kind of soaking it in. There's a lot to take in here.
Okay.
New technology.
No. Yeah. No. Now it's time for discussion. In a general
everybody's pretty quiet. I don't know how many people out there are actually doing measurement on Bluetooth speakers. I know that I am, and I can see a couple of people in attendance who I know are doing Bluetooth measurement. We really struggled with this to begin with. We had one project where our client asked us to measure every Bluetooth, well, I'm not going to say every Bluetooth speaker on the market, but certainly many Bluetooth speakers on the market. And so that's a great database, but boy, that was painful getting it up and running. And then you add to that we're around office personnel and we're around factory personnel, and a large percentage of those factory personnel are listening to Bluetooth speakers. So it was really difficult to connect to our DUT. And at one point we actually had to walk across the street with our test apparatus and then pair the units and then carry the units back to the test lab and then measure them that way. But I don't see too many questions. I don't see any questions out there other than the one.
Maybe in comment what you say, Kent, what's interesting. In the future, not only the loudspeaker is our weak part, it is also the wireless connection with all the dropouts and the other things, and it's the DSP processing. So that means we are looking for those strange distortions, like which are impulsive, which are changing completely the sampling rates, the frequencies, and so on. So we have to be open for those kinds of new distortions, I would say. Very uncommon, right. And in the analog world, we have never seen them. That's the conclusion.
Right.
No?
Right. It can be pretty painful. One of the a great topic out there and coming in as a question is, have you done any measurements using LAN, a network connection, or AVB or Dante?
We are at the moment working a lot with Dante and something like that. It's of course much more stable. It's used for professional application and other things. If you have a cable, the conditions they're much better than wireless connections.
Right, and so you shouldn't really be experiencing any specific distortion or
right.
behavior. I mean, yeah. I guess that's a question when you have a correct direct hookup with Dante. Is the KLIPPEL equipment going to be Dante anytime soon?
Of course, we are working on that. We need this very much for the power testing. We think that Dante is for long-term testing a very nice way to use existing equipment and something like that.
Good. Yeah, I'm seeing more and more of that, of course. So I don't see any other questions coming in. I don't know if you want to summarize, and
yes.
And I'll watch the question window if people are scratching their chins and want to add, but I'll let you summarize.
Yeah. One message is that the wireless digital transmission is usually not perfect. We expect that, but it's not. There's multiple reasons for that. There are actually new nonlinear mechanisms, which are also time variant. It's changing over time. If you're starting again the connection, it is different. It is random. That's close to rub and bus and to those irregular stuff. So accurate testing requires some special precaution. If you are doing that, you are relatively safe. So you can solve your daily work. So we are doing our best. It's our target, our challenge, to smooth it down, to make it almost invisible, to taking care of all that in the best way. Yeah, that was our session. So that means up to now we have spoken a lot about physical measurements. We finished now more or less a physical measurement. And now with the next one, we are coming actually to some perceptual problems, benchmarking problems, rating problems, and defining limits, tolerances, and so on. So we are using more or less the tools provided by the ESA standard and combining that to ensure, with big question, how to ensure sound quality. Yeah. So the benchmarking of audio products under standard conditions, which criteria are important, how to choose the measurement conditions, how compare the measurement results, and how to draw meaningful conclusions for the device. Yeah, and how to use the standard as it is for benchmarking. That's very close to the rating, but here we have more options for doing the benchmarking. Actually, for the rating later on, we need some internal limits it comes later. Here, for the benchmarking, there are also some ways to avoid for a moment limits for THD and other things. So it's a quite interesting topic. Please join it. That's benchmarking of audio product under standard conditions. That's our topics in 1 week.
Wonderful. Well, thanks as always, Wolfgang. Thanks everybody for attending. And don't forget, you can go to www.klippel.de and go to the registration page and scroll down, and you can see all of these sessions and take them in at your leisure. And tell your colleagues about it. Our intention is to spread good information during these times. And I wish you all well. Stay safe. Keep that mask on so we can all get back to normal life. And we'll talk to you next week. Thanks, Wolfgang.
Thanks, Kent. Bye-bye.